So now we have looked at the 5 transistor OTA. So after looking at the 5 transistor OTA, to increase the DC gain, what did we see? We looked at Cascode. So let's look at Cascode first, and then we look at the other OTAs. So let me take an NMOS Cascode. So let us say this is M1, M2. This is where I apply the input. This is some bias voltage. For small signals it is grounded. And let's assume that I have an ideal current source here, biasing this fellow something. This is my Vout. So again, for small signals I can open the current source. So I'll open this. So let's quickly check the poles and zeros here. Okay. So let's start with poles. Again, for pole locations the input doesn't matter, so I'll make the input 0. So again, let's try to lump all the capacitors. So let us say at the output I again have a large capacitor dominated by the load CL. So I have another capacitor here from this node to ground. We call it CL. There will be no other capacitor. All the capacitors you can kind of lump it to these. Cool. So how many poles we have here? 2 poles. So I have 2 poles. So as usual, I'll assume that the load capacitor is much greater than C1. So then how will I proceed for the pole locations? If I assume CL is much greater than the other capacitor, what can be the approximation I can make? The low frequency pole is contributed by, so which means what can I assume for C1 in this case? So which means the pole location is the 1 by the capacitance times the resistance it sees, and we are computing the resistance here when C1 is open. So what is the resistance looking here? GM2 R02 times. So it's basically, I'll write it directly, it is the output conductance by CL. So maybe I'll remark G out is basically 1 by GM2 R02 times R02. So this is first pole. Let me copy paste this. Now I'm looking at a higher frequency pole. And for this, what can I assume for, what can I assume? I can assume that CL is short because I am looking at frequencies beyond this pole location, wherein CL is a short circuit. So again, now it's simple, we have a first order system. So the pole location is trivial, it is 1 by C1 times the resistance it sees. What is the resistance we have looking here? First of all, what is the resistance looking down? R0 of M1. What is the resistance looking up? 1 by GM, because the drain is basically a small signal ground. So this is nicely 1 by GM2. So what is the final output resistance? 1 by GM2 in parallel with, how can you approximate it as? It's approximately 1 by GM2. So this is 1 by GM2. This is basically GM2 by C1. And in this case, I assume that CL is infinity.
In this case, we are open circuit in this current source.
Correct.
What if we consider the transistor instead of?
Yeah, then you have some output resistance due to the current source that is going to come, right? That's all. That means in this case, for the high frequency pole, this is anyway short, doesn't matter. In this case, you have some R out here that will come in parallel with the looking down output resistance. So these are the poles, but again remember we have made an assumption that this is the low frequency pole, this is the high frequency pole. Let's confirm that. I know CL is very large, and the output conductance, will it be a large number or a small number here? It will be small number because the output resistance of the cascode is large. So this is going to be small, this is going to be large. So P1 is going to be a small number, and here I have C1. C1 is a small capacitance compared to CL, and GM is much larger than your conductances. So it is completely fine that we have made this assumption. Again, always remember to verify the assumptions. So here I'll remark that we have verified the assumptions. Okay, so this is only the poles. So let's look at zeros. So again, for zero location, I'll specify the input output. This is my input, this is my output. So can you tell me how many zeros I'll have here? 1, 2, 3, 4. 1. Why? Which capacitor you can short? See? 1. Okay. You're saying you can short this, right? So let us say you short this. You short this, you are applying a voltage here. The transistor will generate a current of what value? GM 1 times Vi. Now where will this current flow to? Everything will flow to the short circuit, nothing flows to the output. So what will be the output in this case? I mean, if I short C1, what will be the output in this case? So is there a 0 in the circuit? Right? So there is no 0 here. We have only 2 poles. So for Cascode, we just saw we have 2 poles and no zeros. Cool. So after looking at the 5 transistor OTA, what did we do to increase the gain? We used, we understood Cascode. Then what was the topology we came up with? Telescopic Cascode. So let me try to draw this here. We'll copy this. We'll briefly look at the poles and zeros there. We'll not go into exact calculation. So, okay, let me see if I can. Erase all of this. So let me see if I can redraw this as such. So I'll draw a telescopic cascode here quickly. So I have a PMOS cascode. Similarly, I need to have an NMOS cascode. And I do this high swing cascode connection. This may be good. So once again we can lump all the capacitors. So let me just do it. I'll not do it in detail, I'll just show you and then we'll move on. So at each node I can consider a capacitor like this. So here I have something. Similarly here I have something. Here I have something. Here I have something, and here also I'll have something. So again, just like in the 5 transistor OTA, I'll make similar assumptions that CL is larger, and I'll also ignore the R0 of the differential pair, the NMOS transistor. So once again, if I ignore R0 of the NMOS transistor, and if I look at differential mode transfer function, what can you say about this common source node? That is 0. So again, we don't have to consider that seriously. So this node is sort of isolated. So again, just tell me the number of poles here. How many poles can I have? I have 6 capacitors. All 6 capacitor voltages can be defined independently. So I'll have 6 poles. But remember, this also technically contributes to an additional pole. So I'll just say +1, but that will get cancelled. And if I make an assumption that CL is much greater than all the other parasitic capacitors, what would you do to proceed? You open all the other capacitors and assume that the low frequency pole is only due to CL. Here I assume all the capacitors to be 0. This is going to be your output conductance by CL. Same thing as before. Now for finding all the other capacitors Pk for k greater than 1, what do you do for CL? You short CL and then you have to try to do it. But again, once you short CL, maybe I'll copy this. So let us say I've shorted CL now. You now have 1, 2, 3, 4, 5. Fifth order system. Once again, you can write the pole as 1 by RC only if the capacitors are uncoupled. So you can actually go and find the if that is the case. For example, if I mark it as C1, C2, C3, C4, C5, you can check maybe if C5 is uncoupled from all the other capacitors, and for checking that you find the resistance seen by C5. We'll write it here, right? Resistance seen by C5 for all combinations of C1, C2, C3, C4, right? So you have going from all zeros to all infinities, you have 16 combinations. You find all 16 equivalent resistances. As long as they are approximately equal, you can say C5 is uncoupled from the rest of it. Similarly, you have to technically do for all the capacitors, right? Just because C5 is uncoupled from C1, C2, C3, C4 doesn't mean C2 is uncoupled from all of them. So you have to do it. And again, you can actually, if you want, you can sit and do. If you do it, it turns out roughly they are uncoupled. So you can roughly write the pole location as the conductance at that node by capacitance at that. Again, this is a nice exercise. You take it as a practice and do it. That will make you thorough with small signal impedances. Yeah.
If we assume that C5 is uncoupled,
yeah.
So if we are moving for C2, so we need to check for C5 also.
Yeah. See, the point is, simple logic, right? You are saying that C5 has is not coupled with C2. I mean C1, C2, C3, C4, C5. This means that C2 and C5 are uncoupled, but we don't know whether C2 is coupled with C1, C3, C4.
So if we are calculating for C2, so we will consider C1, C3.
Yeah, that you can do. But you understand the point, right? Yeah, that's correct.
It will simplify further.
Yeah, exactly. Right, so I mean, you please try to take it as an exercise so that you get more, used to small signal impedances. Again, that's why I have been emphasizing on understanding the small signal impedances, because pole zero locations is basically understanding what is the impedance at this node, what is the capacitance at that node. Right? Okay, so that is the pole, and how many? Let me copy here. How many zeros I'll have here? Can you look at it and tell me? Let me copy paste this. Hold on. Yeah. How many zeros I can have here? Ignore this capacitor. Can you think and find out how many capacitors I can short? Again, remember, this is my output. Don't tell I didn't mention what the output is. How many capacitors I can simultaneously short so that the output is still non-zero? That is the question. Four. Which four? So let me label these guys. Yeah. So now tell me which all capacitors can be shorted. C1, C1, C2, C3, C4. I mean, at least logically it should make sense. I don't need to have the left half to get a non-zero output, right? Because I'm feeding something to the right side half. So even if the left side half is completely gone, I'm fine. So I can short all of these three. Definitely three. Now, can I short C5? We just saw for the cascode. If you short C5, whatever voltage you apply here, that will be converted to a current by this transistor, and all of the current will flow through the short circuit, making the output 0. So I cannot short C5. Can I short CL? This capacitor can also be not shorted, but I can basically short this one. So how many zeros I can have? Yeah, 4 zeros. But again, I'll make a remark that if you include this fellow, that can also be shorted, so that will give rise to an additional 0. Just like the 5 transistor OTA case, if you tend R0 to infinity, this additional pole, additional 0 cancel. Again, finding the 0 location is not really rewarding. So as long as you understand how many zeros are there, that's reasonably good. So once again, here if you try to sketch the differential mode transfer function, you will find that you have one dominant pole, and all the other poles and zeros will occur at much higher frequency. So for practical purposes, you can approximate this as a first order system like this, because all the other poles and zeros typically they occur at much higher frequency, wherein the gain has already dropped a lot, so it's okay. So here also you can approximate this as some DC gain by 1 plus S by P1. And P1 is basically your dominant pole, and if you have a large load capacitor, you can attribute to the dominant pole to the load capacitor and the output conductance you have. Now, not just the telescopic cascode, in fact all the single stage OTS we have seen, all the OTS we have seen so far, the 5 transistor OTA, telescopic, folded cascode, gain boosted cascode, everything is a single stage OTA, which means you have one single transconductor or one gain stage technically, and for all of them you can approximate the behavior as a first order system like this.